In today's question, a cylinder of radius r made of a material of thermal conductive K1 is surrounded by a cylindrical shell of inner radius r and outer radius 2r made of material of thermal conductivity K2. The two ends of the combined system are maintained at two different temperatures. There is no loss of heat across the cylindrical surfaces and system is in steady state. The effective thermal conductivity of the system is. So herein we have to identify first of all how this system is connected, whether they are in series or whether they are in parallel. So let us try to identify the key points based on which we can identify whether the system is connected in series and whether they are connected in parallel. So let us start with our series versus parallel. So first aspect we are going to take into consideration is heat flow direction. Heat flow direction. And for series, this heat flow direction is radial. Or we can say through each layer sequentially. Through each layer sequentially. Now let us see what happens for the parallel. For parallel, it is axial. So which means through you can say through various positions simultaneously. Okay, so you can say simultaneous. Next aspect rather, we are going to take into consideration is it is called as a temperature difference. Temperature difference. For series, the different temperature between the layers. Different temperatures between the layers. So which basically means that is we have T1, then it will be T2, then it will be T3 and so on. Whereas in case of parallel, same temperature difference across all path. Same temperature difference across all paths. So which basically means which basically means T top, temperature at the, you can say, top, and temperature at the bottom. Next aspect we can take is our heat transfer coupling. Here we can say heat transfer capacity rather. Heat transfer capacity. Now in case of series, the heat passes sequentially through all the materials. Heat passes sequentially through all the materials. Whereas in case of parallel, heat flows independently through each component. Heat flows independently through each component, or we can say each part which constitutes the system. And the last is our the conduction part. Last aspect is conduction. So in this case, series, or let me write it, conductor basically. How the conductor is conductor in use, like a type, which type of conductor is being used. So first is our for series. So for series, insulation at the end and no lateral heat flow. Insulation at the end and no lateral heat flow. And for the parallel, it has a uniform axial temperature difference and no radial, you can say, heat flow. For parallel, we can write uniform axial temperature, uniform axial temperature difference. So these are the few aspects which we can keep in mind, and we will be able to identify whether the system is in series or in parallel. Now we come to the given question, and the given question, it is given that R1 and R2 are the thermal radius of inner and outer partition. R1 and R2 are the thermal radius Let me check what they are given. Thermal. Are the radius of inner and outer partition. Outer partition. So we can approximately draw the figure for that. So we have this is not, that is R and 2R, my mistake. Or let me write it R1 and R2, then we can change it much better. So we can, this is our R1 and this will be R2. So we just try the generalized formula, then we substitute the values. And moreover, it is given that since the temperature at both ends is same, temperature at both ends is same, they are in parallel. Are in parallel. Therefore, we can write 1 upon R will be equal to 1 upon R1 plus 1 upon R2. Now we easily can find out what will be our R1, R2 and R. So we can write that our inner area let us call it A1 will be equal to our pi r square. Outer area, let us call that A2 will be equal to, this will be a pi and we have 2r whole square minus r square. And here outer means this part. And if K is the equivalent thermal conductivity of the system, K is the thermal conductivity of the equivalent system, then we can write effective area of the equivalent system, effective area of the equivalent system will be equal to pi 2r square. Now we simply substitute the values. We get this as Ka upon L will be equal to K1 A1 upon L plus K2 A2 upon K2 A2 upon L. And if we substitute the values of A1 A1 A2, we get this as K multiplied by, this comes as 4 pi r square is equal to k multiplied by 4 pi r square, k1 multiplied by pi r square plus k2 multiplied by 3 pi r square. And this pi r square cancels out throughout. So we get this as 4k will be equal to k1 plus 3 times k2. And now it is simple that k is equal to k1 plus 3 times k2 divided by 4. So this is our final answer. And the options that are given to us, if we check them, we can say option is our 3k2, 3k2, 3k2 is option number C is the correct option. So this is the effective thermal capacity of the system. This is effective thermal capacity of the system. And the option that was correct was, I think, C. Yeah, C was the correct option. Option C is correct. So this question was quite simple. Only little bit tricky part will be how to identify whether they are connected in series or they are connected in parallel. Once we are able to identify it, rest things fall into its places quite usually because it is directly related to the formula then. So this completes the question. Thank you.